Good morning, everybody. So, it's for me a pleasure, a real great pleasure to introduce next speaker, so Professor Zamir from Tel Aviv University. So, after BSc, MSc, PhD in Tel Aviv University, he made he has been a research associate at Cornell University, visiting researcher at UC at Santa Barbara, and finally became faculty member at Tel Aviv University, where he's now a professor. So he's well known for his paper with errors achieving a half-log 1 plus SNR on the AWJ channel with Lattice encoding and decoding. This method is widely used now in many papers in information theory when people have to use lattices. And his research interests include information theory, communication, and remote sensing, also signal processing. And for example, he made some famous talks, like this one it was a plenary talk at Lattice 2010, Can Structure Each Random, the story of lattice codes, or some other ones. I like this title, for example, lattices are everywhere. So, and finally, he published a book, Lattice Coding for Signal and Networks, and it should be a very good idea to buy it. It's a very, very interesting book. So, please welcome Professor Zamir.
Good morning. Okay, so thank you for coming to the morning lecture. Although I guess after 2 weeks you're already tired, and it's a great pleasure to come to Brazil. It's my first time in South America, in Brazil, and I took the opportunity even to travel a little bit. I passed in Rio de Janeiro and in Foz do Iguaçu in my way here. It's a beautiful country, and I thank the organizers, in particular to Swelling Costa, which you don't see her, and Marcelo here, who invited me her. That's all right. Okay, so at this point in time, I guess you know so much about lattices that I can really skip the first part of the talk, of the lecture. The only thing is that you will see that the notation is something that everyone uses something else. So I'm using G for generator matrix, and for me people use the M. But besides that, I guess I can skip the first part. And I want to, in the beginning, to say that lattice means different things to different people. In particular, and I like this badge a lot, so I guess it's not okay. You know to take it down.
Take another one.
Another one, okay. It's part of the so you can ask me questions during the talk, and I can ask you. So I guess you know these two people, who they are and what they represent. So in the Information Theory Society, there are two communities, I would say: the Shannon theories and the coding theories. So the first ones are using more probabilistic tools. They talk about mutual information, random codes. They find the limits to performance, and they don't care about complexity. The latter ones construct something. They want to approach the limits that information theory promises. They like, usually the people like algebra, combinatorics, use less probabilistic tools, I think. So these are two different communities. And about myself, so this is what I wanted to be. I started as such a person. 25 years ago, I was doing source coding and information theory. But at a certain point, I felt that sometimes the theory is too abstract, and sometimes the random coding ideas, they hide important things. and that you can see when you start to put structure or geometry to the solutions. And the goal of me in this, actually, it wasn't the goal for 25 years. Lattices in the beginning of my research just came, as they were a secondary issue, but slowly they became prominent in my research, and until it was such an obsession that, as Jean-Claude told you, I did something I never thought I would do, which is writing a book. And so I didn't convert, so I will put it maybe now in the Hamming side. But I'm not really a coding theorist. So what I'm doing, I'm looking on a lattice as a black box, which has some properties. I want to understand which properties are important, and to put this black box into the problems that information theory and the setups that information theory suggests. So this would be the spirit of this and tomorrow's lecture. And people that I guess you heard about that influenced me, influenced the development of lattices and lattice codes in information theory, and why they are important in communication. So I can say give many reasons, but let's indicate 4. So first of all, with a lattice, you can go in the dimension monotonically from 1 to infinity. In digital communication, people usually work with small dimensions, except for a few people in the industry. Most of the people think about the constellation, which is 2-dimensional. This is digital communication for them. And information theory thinks about block length, which is infinity. And we need something to make a bridge between these two extremes, and the lattices can do that, because a lattice exists for any dimension. We will see, actually in tomorrow's lecture, I will talk about multi-user problems. And in multi-user problem, information theory uses the term random binning to solve problems. We will see that lattices gives an algebraic or geometric binning, form of binning, that explains what it means. So this is one good reason for me to use lattices. Also, I use lattices in my research for doing joint source channel coding, so a bridge from analog to digital, you can say. I don't know if I will have time to deal with this in the 2 lectures, but this is an interesting topic, aspect. And the last aspect, which also we'll talk tomorrow, that sometimes lattices even give solutions which are better than what random coding techniques are giving. So it's not, you mentioned this title, can structure bit random. So it's not that structure or lattices bit Shannon, but in some situations the structure is important for the problem to give a better performance. And okay, several special features that you will see. Okay, before that, lattices actually things that we see in information theory, like random coding or randomness. In the lattice case, they have a different reflection, the same as typicality, something a term known in information theories, and binning, as I said before. And with lattices, we will see that we will use the term tethering, and I will explain it. It's a kind of randomization, something that replaces the randomization of information theory. We will use filtering at some points, so minimum mean square error estimation. We will talk about soft versus hard packing of spheres in space, lattices in high dimensions, terms that I will mention in the lectures, nesting, coset, spinning. So we will see them all. And this is the general plan. I also plan to use the board from time to time. There is that. Okay, good job. So one thing that I understood that some people ask exactly where lattices fall in the picture of digital communication. So I'm going to talk also source coding and channel coding. I think till now, mainly the lectures were about channel coding. So if we have, we're talking about source and channel coding. So there is a source, which in the beginning is some signal in time, and we want to transmit it through a channel. So there is somewhere a channel, let's say some kind of additive noise channel, or it can be more general, and we want to produce a certain signal. So let's call this signal S of t and signal X of t, which represent the source in a good way for the channel. And in the end, we need a receiver which reconstructs the source. Now, as it turns out from information theory, one of the important principles is the separation principle, which says that in this problem, which in this problem you see only analog things, analog source, speech, analog signals over the channel. So Shannon showed that the conversion to the digital world doesn't cause any loss. So this is the separation principle of Shannon. So we take the source, we first sample it. So instead of a continuous time source, we have a vector in n-dimensional space, let's say, n samples, a block of source samples, and then we do first source coding. And we get a message or bits. So this is the conversion to the digital world. This is the first half of the transmitter, and the second half is the channel coder, which it would be convenient first to think that it produces a vector of discrete values which are discrete in time, x1 till xn. So this is a vector x in Rn. This is a vector s source in Rn. And after that, there is something that engineers call D2C, which makes convert the samples into some analog signal. Okay, so source coding, channel coding, and the conversion here is from a continuous vector to a message. So it's conversion to the discrete world, and a lattice can represent the points which actually are the points in the end that reconstruct the source. So it's a collection of points as reconstruction, which belongs to a lattice which would be the source coding lattice. So it represents the code words to which we quantize the continuous vector S, and then we can represent these discrete values by bits. And the same thing happened here in the opposite direction. So we have the bits, which, so this lattice, we have here a conversion from S to some discrete vector in lambda source. And here we have a conversion between some point lambda, which is represented by the bits in lambda in the lattice that represent the channel code words. And these are these are the vectors which we are outputting into the D2C and become the signals which are sent over the channel. So maybe then we use the vector X in lambda channel. So just to have a picture where these lattices fit into the picture of digital communication, I hope it is clear, or is it clear? Okay. And in this lecture, we will see both sides of the picture, the source coding side and the channel coding side. But Before jumping into that, let's see what we have in our plan. I will skip most of the definitions which are known. I will talk about figures of merit, how we measure goodness of a lattice. Then I will introduce this notion of dithering and estimation. I will talk a little bit about entropy coding for source coding, entropy coded quantization. I will talk about using a lattice as an infinite constellation, which is how it is shown here. I mean, there is a lattice which has infinite number of points which we can transmit. This is a little bit artificial, but it helps us understand the importance of the figures of merit. Then I will talk about asymptotic goodness, which means how we can show that that lattices of high dimension, the dimension goes to infinity, can approach the limits that Shannon promises within the framework that we will build. And this will also cover error exponent of lattices. And at this point, we will stop today. This is the goal, and then these topics will be covered tomorrow. Okay, so as we said, definitions, the only thing is that you need to notice is that I'm using the notation G. Another thing that I'm sure you saw is that a given lattice has many bases, and they are all related by a unimodular transformation of the generator matrix of the lattice. And the generator matrix, or the basis vectors of the lattice, induce a partition of the space into parallelopipeds. And since there are many bases, then we can have many ways to build these parallelopipeds. And in fact, there are many partitions which go with the lattice, and they all are built on something we call the fundamental cell. The fundamental cell is any set in the space, such that if we translate it by the lattice points, we get covering without overlap of the space. So the most known fundamental cell is actually not the one that is created by the parallelopiped of the basis vectors, but the one that is created by Voronoi partition according to the nearest neighborhood. And I'm sure you saw that. This is the hexagonal lattice and the hexagonal cells that it uses. A few more terms. I'm using the term lattice quantization with respect to a given lattice and a fundamental cell. We say that point X is mapped by the quantizer to a lattice point lambda if X falls in the translation of the fundamental cell by lambda. And this gives rise to the definition of modulo lattice operation with respect to some fundamental cell. It's just the quantization error, the difference between X and the quantized point. And in the case of a Voronoi partition, this modulo lattice operation gives us the vector to the nearest lattice point. But in general, it can be any fundamental cell that uses that. And we have modulo laws, which are the same as modulo in the scalar case. So iterative modulo is enough to have one modulo at the end. And we can also do translation between modulo with respect to different fundamental cell. What matters is the last one. These are simple things. Another thing to notice is that all the fundamental cells are equivalent modulo. A modulo equivalent, what they say, you can take pieces of one cell, shift them by lattice points, and get a perfect construction for the other cell. And there is the notion of a coset, which means the shift of a lattice by some point. And it turns out that the fundamental cell has the nice property that it is a complete set of coset representatives. So for any given fundamental cell, we can say that every coset of a lattice has one unique point inside the fundamental cell. Okay. We can do, when we say Voronoi partition, it can be not necessarily with respect to Euclidean norm, it can be with respect to other norms. For example, fourth power norm give us a different partition. And we can mention also the term of tiling of space. So a lattice is special case of tiling of space, when we do tiling, we allow rotation of the piece that we are tiling with, but with Lattice, we talk only about translations without rotation of the fundamental set. We talk about transformation of a lattice. So we have one lattice, we multiply it by some matrix, we get a different lattice. And it's interesting to note that if we have a parallelopiped partition for the first lattice, and multiplied by the matrix, we get a parallelopiped partition for the transformed lattice. But for the Voronoi partition, this doesn't work. So if we have a Voronoi partition, we multiply the lattice by a matrix A, it wouldn't be, the Voronoi partition of the A times the lattice is not A times the Voronoi partition of the lattice. And last, in the introduction, construction A, you heard it, I think, several times in the lecture. There is an efficient way to build lattices from linear codes, but note that not all lattices in the world can be constructed like that. For example, the hexagonal lattice or the FCC, BCC, the lattices which are famous for in low dimensions cannot be constructed as construction A because the ratios between the length of the basis vectors are not, or the coordinates of the basis vector are irrational. So there is no way to take integers, lift linear code into the integer world and then scale it and to get the hexagonal lattice. Okay, figures of merit. So how we measure goodness of a lattice? And I think so far the main focus was in lecture that you heard, at least was my impression from yesterday, the only day I came here, I was here, is the minimum distance. So the notion of that the lattice can generate a good packing of spheres in the space. And the packing and minimum distance have a simple relation. I mean, the radius of the spheres that you can pack is half the minimum distance of the lattice. But we can mention other notions. And by the way, it's not the only notion. So minimum distance, usually you think about minimum distance as related to probability of error in Gaussian noise. But it's only, as you, I think you saw, it's only approximation for the true expression for the probability of error. And I think you already heard, for example, in Jan Claude's lecture yesterday about lattices, goodness of lattices for secrecy problems, which was something a little bit different about these folded or replicated Gaussians that need to become as flat as possible. But there is also a completely different direction, which is the direction of covering, which is related to source coding. So if in packing we want to pack as many spheres as possible of a given radius in a certain region in space, in covering we want to find the minimum number of spheres in order to cover every point in space. And by the way, you don't have to enforce that the packing or covering will be based on the lattice. The centers of the spheres maybe can be located not on the lattice, but we can limit the discussion. And so far until today, there is no example where people can say, a dimension for which it is known that the best packing or the best covering is, which is non-lattice based, is strictly better than lattice-based packing or covering. Okay, so another thing to note is that if we care about the optimal lattice, so the optimal lattice for packing and for covering is usually not the same. In 2 dimensions, it's the same. The hexagonal lattice is the best packing and covering, and also is the best for many other measures. But even in 3 dimensions, the best 3-dimensional packing is a lattice known as FCC. This is the best way to put oranges, let's say, in the file. But the best 3-dimensional the covering lattice is the BCC, it's a different lattice, and this is the best way if you want to allocate base stations in a, think about a skyscraper, a big building, and you need three-dimensional covering by base stations or access points for Wi-Fi, and we look for the minimum number of such stations. Each one has its covering radius. Then the best location of the station wouldn't be according to the FCC lattice, but according to the BCC lattice. And in higher dimension, even the best lattice is not known usually, but still it is interesting to understand that the best for different questions is different. How can we measure efficiency? So covering, okay, so it would be good to take the Voronoi cell, put the sphere that is the largest sphere inside it, inscribed in it, and circumscribe the sphere, which is the smallest sphere that will be outside it, sphere or a ball, using the terms the use of for the same thing. And so we can define the covering radius of the Voronoi cell, which would be would represent covering of space by balls, where the spheres, the balls are located on the centered on the lattice. And we can define the backing radius, which is, as I said, minimum distance divided by 2. And we can also define effective radius, which is a radius which is somewhere in between. If the radius of the ball having the same volume as the volume of the Voronoi cell. And I forgot to mention, all the fundamental cell of the lattice must have the same volume, otherwise we will have a contradiction, right? And this volume is the determinant, the absolute determinant of the generator matrix of the lattice. Okay. So if we have this volume, we can find a sphere, a radius of a sphere or a ball, which has the same volume, and this is the effective radius. And then we define the covering efficiency as the ratio of R covering to R effective. It is always greater than 1, but we want it to be as close to 1 as possible, which means efficient covering. And the packing efficiency, which is R packing divided by R effective, it is smaller than 1, and we would like it to be as close to 1 as possible for effective packing. Okay. But from engineering point of view, packing and covering are not exactly what we want. We talk about source coding, which is quantization, the quantization problem, and channel coding, which is the modulation problem. So in source coding, we quantize by the lattice, and we care about the distortion. Distortion usually is measured by mean squared error. So we look on the quantization error, which is the difference between the original vector, in this picture it was S, and S hat, which S was the true source, and S hat was the point in the lattice. And when we ask what is the average mean squared value of the difference, okay? Now, if the source has a density which is very smooth, and the lattice points are dense enough, then we can say that the quantization error is roughly uniform over the cell that the quantizer used. If it would use the Voronoi cell, it would be uniform over this Voronoi cell, and the distortion would be simply the second moment of the vector which is uniform over the Voronoi cell. And it's good to normalize by the dimension, so we can think about distortion per dimension. But then we get something which varies by scaling, and we want a measure which is something inherent to the lattice and non-sensitive to scaling. So what we do, we divide by the volume of the lattice, as we said, the determinant, absolute determinant of the generator matrix, raised to the power of 2 over n. So we get a dimensionless number, and this is, we call it normalized second moment. It represents efficiency of the lattice for quantization. And this is close to covering, but not exactly. For modulation, in modulation, we usually, in the Gaussian, of course, yes.
So Voronoi region is defined for Euclidean, or can
Right.
you define, like, are there?
Yeah, sure. You can define it for, as I said, for Voronoi regions with respect to other nodes or other measures, and then you can, yeah. So you can, this is why it is important to understand that the partition is not unique. But what is common to all partitions is that the volume of the cells is the same, and it is invariant to the partition. But the partition can depend on your distortion measure. You use Voronoi partition, parallel Whitehead partition, Voronoi with respect to Euclidean, Voronoi with respect to some other measure. Okay. So in modulation, we care about things, about signal-to-noise ratio, how much power we waste in transmission, and about probability of error. Okay. But with the lattice, if we do not limit the lattice, we bound it in a finite region in space, the lattice is unbounded and represents infinite power. So we cannot talk about signal-to-noise ratio. Instead of that, we use the term volume-to-noise ratio. And again, to get something which is dimensionless, or at least not dimensionless, but something which has a meaning, we take the volume of the lattice cells raised to the power of 2 over n. I hope it is clear that the volume is a quantity which is like centimeters to the power of n. So we take, when we raise it to the power of 2 over n, we get something which is like squared length, and we divide it by the sigma square, which represents the variance of the Gaussian noise, and we get something called volume to noise ratio. But then we have this probability of error. Usually in digital communication, when we build this part, and by the way, the suppression principle is very important in the industry because it means that some companies are expert in doing this part, and some are expert in doing this part, and they don't talk to each other. They only need to define the interface by bits. But in any case, when we build this block, usually it's convenient to specify what is the target probability of error. And when we specify that, we scale the lattice until we satisfy this target. And what it means, a good decoder uses maximum likelihood decoding. If we're talking about Gaussian noise, maximum likelihood decoding corresponds to nearest neighbor or to Voronoi cells. And an error will occur when the noise leaves the Voronoi cell of the lattice. So we define the probability of error as the probability that the Gaussian vector goes outside the Voronoi cell. And we scale the lattice until we get the desired probability of error. And then when we scale it, or we can scale the noise, it doesn't matter. We can scale the variance of the noise until we satisfy it. And then we calculate the volume to noise ratio at this probability of error, and we call it the normalized volume to noise ratio, NVNR, of the lattice at probability of error PE. And this would play the role of efficiency for the modulation problem. And actually, this is not on the slides, but there is something which relates the packing covering efficiencies and the quantization and modulation efficiencies. So we can show that G of lambda is always better, it is always worse. So it's higher than G of a ball, n-dimensional ball. Let's call it ball n. So the lattice is a lattice in the n-dimensional space. Let's always work with n for the dimension. So the normalized second moment of a lattice is always worse than the normalized second moment of a ball, which is the same definition, the variance of a uniform distribution over a ball divided by the volume raised to the power of 2 over n. But it is better than this quantity. And here I'll put the row covering, covering of the lattice lambda. And similarly, U lambda PE, the normalized volume to noise ratio of the lattice, is worse than the view of a ball and TE, and it is better than this quantity divided by rho packing of lambda. So it's my turn to ask questions. So how do we prove that the ball is better than a lattice cell? So if we have a lattice cell with a certain volume, and then we can take a ball of the same volume, and I calculate the second moment of uniform distribution over each of them. So what do we know? Okay, so let's ask it differently. If we ask among all shapes in n-dimensional space, which one has the all shapes of a given volume in n-dimensional space, which one has the smallest diameter? If the isoperimetric inequality, right? So there is the isoperimetric inequality, which says that the ball is like always better than all other shapes in terms of diameter, second moment of uniform distribution, and also if we talk about modulation, the probability that Gaussian noise leaves the ball is smaller than any other shapes with the same volume. And this is how we get these two. So these are isoperimetric inequalities, and these ones come just by drawing this picture of the Voronoi cell, the ball inside it, the ball outside it, and we can convince ourselves easily that the probability that the Gaussian noise leaves the ball inside the Voronoi cell is larger than that of the Voronoi cell, and this is how we get this inequality. So you see that if we could make these quantities equal to 1, it means that the Voronoi cell can become similar to a ball, and this would be our target. And we can achieve our target in two extremes. Which extremes? In dimension 1, because then the Voronoi cell is a ball, and in dimension infinity, but not in any dimension in between. So we will see this thing later. Okay, in one-dimensional example, it's easy to compute the normalized second moment for a scalar lattice and discover that this is 1/12. And also, it's not hard to compute the normalized volume to noise ratio for a scalar lattice using the Q function, and we can get that this quantity is given by this formula. It depends on the probability of error, but it is invariant to the size of the lattice, the delta here, the step of the lattice, because we normalize it in the right way. And we can do a calculation if we want to consider higher dimensional lattice. We can draw curves of probability of error as a function of the volume to noise ratio. So the x-axis can be measured usually in dB instead of signal to noise ratio, volume to noise ratio. And then after we draw this curve, we say, okay, we care about probability of error of this level. And then at the intersection, we draw a line that they give us the volume to noise ratio for which this lattice satisfies the target probability of error. And if we increase the dimension and take better lattices, as the dimension goes to infinity, the curve of probability of error versus volume to noise ratio will have a cliff, or it will be like it will have the property that for smaller, for volume to noise ratio smaller than a certain value, it is 1, probability of error 1, and above it is 0, so we have the threshold effect, and this mu star will turn out to be 2 pi e. Okay, so but this is too early in this talk, so we wonder what these quantities converge to as the dimension goes to infinity, and we will talk about it later. This the table of the values of normalized second moment and volume to noise ratio. By the way, it's easy to define. I mean, it's easier, instead of working with these quantities, to say what is the coding gain of the lattice relative to the square lattice, to the Cn lattice, and then define a coding gain or a quantization gain, which is this ratio, and you measure this ratio in dB, and these are the numbers in this table, are coding gain and quantization gain in dB. But I don't want to talk about increasing the dimension at this point, because there are more fundamental things I would like to talk about first. And I said I promised you to talk about jitter, or why we add noise when we use lattices. First for quantization, and then we will discover that it is also useful for us to add noise in channel coding. And this noise is known as jitter. So jitter originally was used for perceptual reasons in quantization. So in picture coding or in picture coding, video coding, it turns out that sometimes it's good to add some noise to the picture before doing quantization, which is strange. I mean, in the end, in communication, we find noise, so why to add noise? And I heard this story, I don't know if this was the inspiration to the engineers in Bell Labs in the 60s, but that in the Second World War there was a mechanical, there was an airborne computer, and at that time there was no electronics, so it was a mechanical computer. And it turns out that the computer worked better in the air than in the lab. And the reason was that in the air, I mean, what was the reason? Someone can guess?
Vibration.
Well, the vibration of the airplane, they avoid probably some, the wheels, some of them get stuck, and the vibration of the airplane helped it work better. So mechanical engineers realized that it's good to vibrate, and electrical engineers also understood that if the picture has small, slow changes, then because of if the quantization is coarse, there are large differences between the levels because you want to work at low rate, then suddenly there is a jump, and you don't want to see this jump with your eyes. So by adding noise, you can smooth out these jumps. But these are perceptual reasons why to use jitter. We will use jitter for analytical reasons, and also it has also practical meaning too. So we talk about jitter. Jitter is represented by the letter U, which is subtractive jitter. So it is something which is not noise, but it's a pseudo-random noise. It is known both at the encoder and the decoder. The encoder adds the jitter before quantizing X, which X is the source, and the decoder subtracts the jitter before sending it to the display or reconstruction. And this amounts, if we are using a lattice quantizer, to a shift of the lattice by the vector U. So it's a coset of the lattice, you can say. And if the jitter is noise, namely it is random, it means that we're taking a random shift of the lattice. And an important property, which we call the crypto lemma, the name was suggested by Forney because it plays a similar role with the key in crypto systems, is that if the jitter is uniform over the fundamental cell of the lattice quantizer, then also the quantization error, which is X plus U modulo lambda, as we said before, would be uniform over the fundamental cell invariant of the input, invariant of X. And the engineers in the audience, the electrical engineers, maybe they remember that when we analyze quantization systems, it's complicated to work with the quantizer, which is a nonlinear device. And it's easier to think about quantization processes adding noise. People like to say quantization noise, but it is not true that quantization amounts to adding noise. it is a deterministic function, and sometimes it doesn't cause any error, and sometimes it causes large error depending on the value. But with jitter, this is correct. So quantization error is something which is like noise. It's uniform over the cell, and it is independent of the input. And why so? I mean, the proof is similar to how you this following argument in a group. So if you have a group, you have an addition inside the group, and we ask what is the distribution of an element of the group plus a random variable which is uniform over the group. So if we are in a finite group, the distribution of the sum would be also uniform. And here, the group is the fundamental cell. The modulo operation, addition modulo the lattice is the addition operation of the group, and we have this property. And as another said for quantization, this is the source coding people are very happy with this property, so they can represent the process of quantizing. If we add jitter before, do quantization, and then subtract. Just amounts to taking the input and adding noise which is independent of the input. So, for example, we know the output distribution is just a convolution of the density of the input and the density of the noise, etc. So this is very useful. But one thing may seem hard in the application. So if you have a multi-dimensional lattice quantizer and we wanted to generate a jitter, it means we need the uniform distribution over a Voronoi cell. This is complicated. So we know modulo operation actually can be easy operation or a hard operation depending on the cell. If it is a parallelopiped cell, it is easy to do modulo operation. You can do transformation, do quantization coordinate by coordinate, and then do the transformation again. This is easy. But Voronoi cell modulo operation is hard because it amounts to finding the nearest lattice point, and we know that this is a hard problem. So it turns out that the jitter can have the same nice property which we call generalized jitter. U is a good generalized jitter if it satisfies this property that S plus U modulo lambda is uniform over the cell invariant to S. And it turns out we can satisfy this property for many simpler distribution of the jitter. And what I will tell you is three equivalent statements. So U is a good jitter, or generalized jitter, if and only if it satisfies that after taking modulo operation it is uniform. So it doesn't have to be originally uniform, it just has to satisfy this. Or equivalently, if we take the distribution of the jitter, the density of the jitter, and we replicate it by the lattice point, as Jean-Claude did yesterday with the Gaussian, but now we do it with the jitter. If after replication, after doing this sum, we get something which is flat, then this is the generalized jitter which satisfies this property. And lastly, and this is again, all are equivalent, if we take the characteristic function of the jitter distribution, which is like the Fourier transform of the jitter distribution, and we look how its values on the dual lattice. If it is 0 on all the dual lattice points except on the 0 point, then it is a good jitter. And actually all these, as I said, all these three properties are the same, actually are equivalent. And using these properties, it turns out that, so let's skip that. And, yeah.
Can you give an definition for the third
so it's actually related to this replication and what happens when you take Fourier transform. So Fourier transform of replication amounts to sampling in the Fourier domain. And so it's like we take all this picture to the Fourier domain and then as we know in one-dimensional signals, sampling in time, I don't know, I mean, these terms are clear to the electrical engineers, I'm not sure to the computer scientists, but sampling in time amounts to replication in the frequency domain, and replication in time amounts to sampling in the frequency domain. This is in one dimension. In multi-dimension, we can have the same properties, but then what is replication? Replication is by a lattice, and when we go to the other domain, it becomes, let's say, it becomes sampling in the dual lattice. So the dual lattice is what you get when you do the Fourier transform. So these are, I mean, actually it's quite easy to get it, but maybe not in class in this.
Just kind of quick question, that is jitter was only for convenience of analysis, or if it's actually helps?
Okay, I always I get this question, and I will address it. Okay, I mean this is a question I'm used to. The first time I was asked, I was a little bit confused, but I have a good answer. I hope.
I have another question.
Yeah.
Suppose that you have to generate a good data. What do you suggest?
Okay. Yeah. So for example, construction A lattices. The best thing is for construction A lattices. So it turns out that you get this, flat after replication if you just take uniform over the cube according to which you did the construction A. So if it's we had a QRE linear code, you lift it to the Euclidean space by adding, replicating it on the Cn lattice times Q. Now take the detail to be uniform over the cube of edge Q, and this will do the job. So this is what he said here. Also, what he said is that it's okay to take detail which is uniform over the parallelepiped cell, even if you are using Voronoi cell in the quantizer, etc. So, I mean, using this theorem, it is easy to find easily generated jitters. Okay, so jitter is something simple to use, as long as you are willing to have pseudo-randomness which is shared by the encoder and the decoder. Okay, one property which I want to mention about jitter is that a good jitter, a jitter of a good lattice is white. What does it mean it's white? It is white. The components of the jitter have the same variance and are uncorrelated. Now you can say this is strange. So an hexagonal lattice is a good lattice, right? It's the best lattice in 2 dimensions. Are these two components independent? The components of a uniform distribution over a hexagonal cell, they are not independent, right? I mean, if I know that I'm here, the x-axis, I cannot be here on the y-axis. But they are uncorrelated and they have the same variance. And this is shared by the best lattice for quantization in each dimension satisfied that the jitter is a white vector, white, not white Gaussian, but white. And the proof is by the property that if it is not, you can improve the normalized second moment by transformation of the lattice and followed by Voronoi partition. It's not complicated. And but now we know that source coding quantization it amounts to adding noise, which is additive, it's independent of the input, and it is white. And if we know the second order statistics of the noise, this invites the use of Wiener filtering. And in the memoryless case, Wiener filtering amounts to multiplying by a scalar. And these scalars can reduce the distortion from the second moment of the lattice to this harmonic average between the second moment of the lattice and the variance of the source. And this is a nice trick that works in several places, and in the end it will lead us up to this result that Jean-Claude mentioned about achieving half log 1 plus SNR. Okay, so we talked about dithering and estimation in quantization, and this can be a good time to talk about entropy coding. Time is running, so let me give you first an overview of these two topics, the entropy coding and the infinite constellation. So using a lattice as a code or code book it seems as a little bit artificial. So in source coding, we take a source vector and we want to translate it into a finite word length in bits, which means a finite number of code words. So we usually say that the number of code words is 2 to the power of n times r, where r is the rate in bits per sample or per channel use. But Lattice has countably infinite number of points, number of code words. So what are we talking about? Working with infinite rate. And the same question may arise in the channel using a lattice for channel coding. So we have messages that we are representing by vectors, the vectors of the lattice. And again, if we take the unbounded lattice, then there are infinite number of messages, so the rate is infinite. So it seems artificial in this way. And eventually we're going to bound the lattice to take a finite portion, but before that we can do something which is a little bit more clever maybe. And in source coding this is entropy coding, in channel coding it's something we call non-equiprobable signaling. And the idea is that we don't have to work at fixed rate, we can work with variable rate. So for example, suppose just scalar quantizer with an infinite lattice, I take Gaussian source and I am quantizing the source by the lattice. So we can move to this side. So we have a scalar lattice, and this is 0, minus delta, plus delta, etc. And we have the Gaussian distribution with the infinite support. We quantize it, let's say for every partition, to the nearest lattice point. So this is would be the probability that we get the 0 point. This would be the probability that we get minus delta. This is the probability we get plus delta, etc. So we have infinite, countably infinite points, and we want to represent these points by bits. And thank you. And just to be fair to be also that on this side. So in source coding, there is something which is very common. It's entropy coding. In picture coding, we use Huffman coding, for example. I guess all of you heard about Huffman coding. And then the rate is that we want to approach the entropy of the quantizer when it is applied to the source X. So there is a source. The quantizer can be a lattice quantizer. After quantization, we get a discrete source, and we want to approach the entropy of this source, which is sigma pi log pi, and the I here is I equals 0, I equals 1, I equals minus 1, etc. And this quantity can be finite even if we sum over infinite number of points. So, and this means, I mean, in practice it means that we are not working with fixed rate, but each lattice point is represented by another, a code word of a different length in bits. The most probable points we get short descriptions. The rare points we get long description, and the length of the description is roughly log over. Oops. Don't tell me that I'm doing here good mistake. So it should be like that, right? Or minus here. And so we can always achieve with the Huffman code something which is like putting the roundings to the nearest integer above. But let's forget about this rounding loss. Then we get we can aim to achieve this ideal quantity of entropy, and this represents the length of the code word, which is assigned to a point with probability pi. Okay, and the same. So we can use an infinite lattice for quantization, provided that we are doing entropy coding, and the same trick in reverse would work in transmission. instead of working with finite number of messages, we will think about the information as a sequence of infinite bits, and we will apply a parsing rule which is similar to what does Huffman code at the decoder. It gets bits and it parses them into code words of varying length and map them into, in the case of quantization, to lattice points. So in transmission, we will get the information, we will pass them according to a valid parsing rule, which is like a Huffman decoder, into code words of variable length. And this is how we will get the points of the lattice for transmission. And each point will get a different probability of occurrence. What is the probability that a lattice point would be transmitted if we are using a variable length code word? Let's assume that the bits, the information bits are IID Bernoulli half. So each bit is independent of the others, and it's 0 and 1 is probability 1/2. So the probability that we get a lattice point, which is, represents a code word of length L, is 2 to the power minus L. So we can, in this way, we can shape the probabilities of the lattice points in transmission, and we can make sure that that the power is finite. This is one important issue, and the other thing is that the rate is just the average length of the code words, which is again finite by looking on the same as in entropy coding for source coding. So I hope this was clear. I mean, I will pass now on the slides, but this is the main idea: how to use an infinite lattice without what is the term, the professional term is shaping, without cutting a finite portion of the lattice. Okay. So entropy coding. So as I said, we take the same picture of linear quantization, but we do entropy coding for the output of the lattice quantizer. This means that each point, let's say the hexagonal lattice, each point gets a different probability according to the probabilities, a different word length according to the probabilities that are induced by the distribution of the source over the lattice. And there is a nice result which says that if I'm calculating the entropy of lattice quantizer of x plus the jitter given the jitter, so conditional entropy, remember it's like a regular entropy, but the condition, since the jitter is assumed to be known on both sides, we can condition on it. So it means that for each value of the jitter, the code book may be slightly different, depending on the distribution of the shifted lattice and the source. And this entropy is equal to the mutual information in this equivalent channel that I mentioned before. So this additive channel is not only represents the jitter quantization in terms of the distribution of x and x hat, the joint distribution of x and x hat, but it also gives us a simple expression for the entropy rate of the quantizer. It's just the mutual information between the input and output of this channel. And the proof is actually not complicated, we just don't have time, but Antonio can give you the book, and there is this derivation. It's very simple derivation of this entropy. But now that we know that we can relate easily the results to information theory, because we have mutual information, so the Shannon people are happy, and they can show that the rate, this rate of the quantizer is half log 1 plus the variance of the source divided by the distortion plus a loss term, which is half log 2 pi e g. So g is the normalized second moment of the quantizer, 2 pi e we will mention in a minute, and 1 is another loss, because we know that rate distortion in theory tells us that the best rate you can achieve for encoding a Gaussian source is half log this ratio without the 1. So we have a penalty here and a penalty here. So this So let's talk about each of them. This penalty can go to 0 if the normalized second moment can go to 1 over 2 pi e. And it turns out, as we will see, that for good lattices, indeed this is happens, so we can get rid of this quantity. And what about the 1? The 1 we can get rid of if we do use winner estimation, which I mentioned before. If we put here this winner estimation, then the magic of the slight reduction in distortion due to this winner estimation, which I mentioned before, getting the harmonic average between second moment of the lattice and the parents of the source, we get rid of the 1. Okay, so it means that with entropy coded detailed lattice quantization, we can approach the rate distortion function if the normalized second moment can go to 1 over 2 pi e. And this is variable rate transmission in source coding. Is the detail really necessary? Okay. Okay. So as we said, detail amounts to shift of the lattice. Okay. So when we calculate average and conditional entropy, we actually average over the condition, over the detail. But we can say no. We will draw a picture of the entropy and the distortion as a function of the value of the detail. And for each value of theta, we will get a point in this plane. And as we move, increase the theta, we start to get a certain curve. But this curve must be closed after we finish the step size, right? And it's more complicated to draw it for multi-dimensional lattice, but something similar happens. When the theta is, the cell size is small, these circles are little. When the cell size is large, these circles or curves are large. And the average performance is some kind of eccentric. Okay? Now, so it means that for any slope in the rate distortion plane, there is a best theta. I don't know if the slope is like that. I can take this point and not this. So there is a certain theta which is better than others. But we know that if we let the dimension go to infinity and we take good lattices, we achieve the rate distortion function on the average. So it means that when the dimension goes to infinity, we cannot have these open curves, because then it would mean that the centroid of the curve is optimal, but there are better points which are to the left. In the source coding we want to compress. So it must mean that for high-dimensional lattices, the curves shrink to a point. Otherwise, we get a contradiction, which means that almost all theta values are optimal. Not necessarily the 0 value, but almost all theta values are optimal. So you don't need to use pseudo-random noise really. Just you select a good vector, a good shift, and you work with it forever. If the lattice is high-dimensional. In one dimension, it's a different story. There is a certain shift which is optimal and it depends on the source, etc. Okay, this may be complicated, but I really want to get to the issue. Okay, let's skip applications of ECDQ because it's a computation. Infinite constellation. I want to talk about the approaches. So I can talk about unbounded lattice. I can talk about, and if I in the analysis, in this case, we get a loss term, which is the LVNR appears, and again, 2 pi e. I can talk about the unbounded lattice. I can talk about probabilistic shaping, which I mentioned before, which is like using variable rate transmission. And I can talk about shaping. And about shaping into finite region in space, I will talk about tomorrow. So let's see for a minute the variable rate transmission. So as I said, we look on the information as an infinite sequence of bits. There is a variable length passing of these bits according to some rule. And the rule is like what we call a prefix code in source coding. So we must satisfy that there is a unique way to parse the bits and a certain average length. And each point of the lattice gets a different probability. It's transmitted with a different probability, and we get a certain shaping of the points so that we will have and then transmit them on a noisy channel. We have finite power. We have probability of error. And we can calculate the power. We can calculate the rate. And we can discover that what we get, the average rate is half log SNR minus this term. Now compare this to what we know about from information theory, the capacity of Gaussian channel, C equals half log of 1 plus SNR. Thank you. So again, we are losing. This time we don't have 1, we want the 1, and we have this loss term. So again, let's talk about it for a minute. If we will have lattices for which the normalized volume to noise ratio can go to 2 pi e, then we get rid of this loss term. And what about this one? In source coding, we use winner filtering. What can we do now? So what I'm claiming is that the decoding can be improved. So what I did here, I made a picture of the Voronoi partition, so in decoding to the nearest lattice point. But I'm claiming that we can do a little bit better. So let us recall digital communication class. We say that optimum decoding is maximum likelihood decoding, and for Gaussian noise, maximum likelihood translated to minimum distance, we get Voronoi partition. So where is the catch? There again. What? Exactly. Okay, right. So the best, actually the best rule for decoding is maximum a posteriori. But if the messages are equally likely, this becomes maximum likelihood. But here, the messages are not equally likely, and then the maximum likelihood is not true. The Voronoi partition should be modified, and again this picture. This is still, actually it is a conjecture, so it seems that map decoding can give us the same benefit as winner filtering in the previous problem, but it's not, the proof is not complete, let's say, not rigorously proved, but if it is equivalent to winner filtering, then we get the 1 and we get the capacity. Okay, and now, last 10 minutes, I will start the next file. So I have 3 files. So most of the second file will go to tomorrow. Asymptotic goodness. So why there are lattices which can close this gap to 2 pi e? How do we know that there are lattices whose normalized second moment goes to 1 over 2 pi e and normalized volume to noise ratio goes to 2 pi e? So, by the way, where do we see 2 pi e in our field? When did you see in the lectures 2 pi e? Which is, by the way, about 70. Information channel theorist, where do we see 2 pi e? So the entropy, differential entropy of Gaussian half log 2 pi e sigma squared. Also, from I don't know if it's more mathematics, but the volume of an n-dimensional ball, Vn with radius r, is given by r squared, r to the power of n, times a quantity which I will denote Vn. So this is the volume of a unit radius n-dimensional ball, and Vn is equal, if n is equal 1, then it turns out to be just 2. if n is equal to 2, then it is the volume of a circle, area of a circle, pi, right, or 3 pi. And then, if we continue, it is possible to see that in the limit it behaves like 2 pi e over n to the power of n over 2. So it actually goes to 0, but this is the way it is going to 0, this coefficient. So this coefficient appears also in relation to balls. And is there a relation between balls and Gaussian? The typical set of Gaussian IIDZ, white Gaussians, is a ball. And this is how we actually, so this is what I call the 2 pi e connection. So there is a connection between white Gaussian noise, between n-dimensional balls, and between the Voronoi cell of good lattices as the dimension n goes to infinity. And it's too much to say in the last 5 minutes, but the connection in this edge of the triangle is AEP, as Tony mentioned. The connection here is the isoperimetric inequality that we saw before. That the ball is always a little bit better, isn't better than any shape, but with Voronoi cells of good lattices, it turned out to be, they are almost equivalent, and this also will close this edge. Okay, so Shannon AEP, typical set, you know, Gaussian becomes, actually it becomes uniform over a spherical shell, but a spherical shell and a ball are almost equivalent as the dimension goes to infinity. So all the volume of the ball falls on the shell. It's also possible to prove to the other direction. If we take a uniform distribution over a ball and we project it over one axis, namely we take integration over n-1 coordinates except 1, then the distribution that we will get from this integration converges to Gaussian. And we don't have only to one coordinate, we can do a projection over 2 coordinates, and we will get two components which become IAD Gaussian, etc. So it works also in the other direction. Isoperimetric inequality we mentioned, we can skip. In order to show the last edge, the one that is here with the question mark, I will need more time, but just to tell you is that the basic idea is that we want to build an ensemble of random lattices. So instead of you working with random codes as Shannon theories work, we will work with random lattices. How to generate random lattice? There are several methods. There is a famous theorem in mathematics, the Minkowski-Halavka theorem, which suggests one way to generate a lattice in a continuous fashion. Here in our context, it would be better to talk about, where was it? About random construction A. I think it was here. We can generate random lattices by fixing the alphabet size as Q, take a random code, linear code over QRE alphabet, lift it to the Euclidean space, get a random lattice, and then average the performance over all codes. Then we will have to take Q to infinity if we want to achieve exactly the best performance, and then dimension to infinity. So we need to take two things to infinity. It may seem very complicated in practice, but if we talk about practice, even with Q equal 2, we can get almost the best performance. We are not far from the best performance, or even with a small alphabet. We don't need to really have a continuously random ensemble of lattices. But with these lattices, indeed it turns out that such lattices satisfy that the covering efficiency goes to 1 on the average of this ensemble. And if we get something on the average, it means that there exists at least one lattice which is at least as good as the average. So there must be one sequence of lattices that whose covering efficiency goes to 1. Let's keep this. Normalized second moment, this implies that the normalized second moment goes to the normalized second moment of a ball, which is 1 over 2 pi e. And the same for the modulation efficiency, it goes to 2 pi e. The only thing that doesn't behave nicely is packing. There is a gap between optimal modulation. Optimal modulation amounts to packing of Gaussian balls, but it is soft packing. We allow a little bit of error probability. Packing of balls is hard packing, and it turns out with hard packing we cannot achieve the 1 that we wanted. We can only guarantee that we achieve half. Okay? So this gap is known as some gap between two bounds in linear codes, the Brashanov-Gilbert bound, the Hamming bound in linear codes. It's still an open question, but we know that there are no lattices which at high dimension can achieve packing efficiency which is better than 0.6, and the conjecture is that indeed what you can achieve is 1/2. Okay, so there is, although the picture seems very nice, there's still something strange here that it is not perfect in all aspects. So I think it's a good point to stop today, and tomorrow, maybe just as a promo, I will mention a little bit error exponent, but then mainly I will talk about nested lattices, lattice shaping that I mentioned several times today, and then I will talk about multi-user problems for which lattices are good, site information problems, and Gaussian networks. We have to get questions, and if you are tired now, we can do it over the break.